Right, hello, hello, hello. Welcome to week 10, Physics 1006. I hope you guys are good. Great job on the test there. I'm just going to move forward because this is an awfully long, and I'm going to try and get through this as much as fast as we can in a good way. So, here we go. Electricity. What do you think of when you think of electricity? And, there's the plug, lightning. We've got electricity there going through the wires and the power grid. Even this cutie patootie there, you see the hair. All right. Do the same thing if you rub a balloon against the head, right? And we're gonna hit on all these there today in some fashion. It's an important topic that everyone should know about anyway. An electric charge is an inherent physical property, okay, and of protons and electrons for sure. Now, protons have a positive charge. Electrons there, they have a negative charge. And charge is denoted by a small q, okay? The SI unit of charge is the coulomb. And you'll see there a big C. And this one here is a good one to know. It's written on your formula sheet, okay? One electron or one proton has a charge of 1.6 times 10 to the negative 19 coulombs. That's a constant. So electrons, that would be negative 1.6. Protons, that would be positive. Like mass, electric charge is fundamental throughout all matter. And unlike mass, there are two types of charges. There's a positive and negative charge. Not so with mass. A little bit of a atom review. You guys can read through this there when you get a chance. You know what I mean? It's a review of 1008 Chem and 1009. And just talking about the proton, the neutron, the electron. The whole premise of what an ion is, right? An ion is an atom or group of atoms with a charge. So you guys can have a look at that one there. Let's just have a look there. Fun with a balloon. Take a balloon and some wool. Tie a rope to the balloon and suspend it. Rub the wool on the balloon. What will happen? Wow. So now the balloon is attracted there to the wool, which apparently looks like a cloud. Very good. What if you bring two charged balloons together? Aha. You can see in the other window because I have the window open here. Of course, if they're both negative, they will repel. If they're both positive, they will both repel. Okay? Why is the balloon attracted there to the wool? Just going back 2 slides. You can say that the wool and the balloon have unlike charges. Okay? Positive, negative will attract. And why do the balloons repel each other here? Because they have the same charge. All right? That's what's going on here. They have the same charge, so they try and get away from each other. Where do you see this? Cling wrap, right? Just the whole idea where using electrostatic forces, we're able there to keep the saran wrap or plastic wrap onto the bowl so that it makes a nice tight seal. Van der Graaf's generator.
Using a Van de Graaff generator, we can safely make a person's hair stand on end. When our volunteer is insulated from the ground, the Van de Graaff generator transfers charge to her body, which her body and hair store. Because it has an excess of one kind of charge, and because like charges repel, each hair is repelled from the others. The hair roughly indicates the direction of the electric field.
Interesting. Hey. Why isn't that working? Would you like us to embed all linked media and convert? No. There we go.
This is called the Van de Graaff generator. It's named after a person by the name of Robert J. All right, we be learning this stuff. All right. Now what we're going to do here, it's talked about in the textbook. It turns out this belt is going to carry charges from little lightning points here, deposit them up in here, and we're going to build up an enormous charge on the top. Let me show you what I mean. Notice notice that I am keeping this closer to the dome than my head. Guess why? I don't want to put my head closer than this, all right? Now let me show you that does charge. Let's try this, gang.
Very good. So you see, what is moving from here onto this person? Protons aren't really moving. Not ever. Well, I shouldn't say not ever, but not in this case. Electricity is electrons. They are moving and going up here. They're filling up the hair, and you can see that even the individual hairs don't want to be around another hair because they're all negative and they're all repelling each other because they're all from the same charge. Conservation of charge. Whenever something is charged, no electrons are created or destroyed. The electrons are simply transferred from one material to another. So you look at this case here, diagram 1. 2 metal spheres are mounted on an insulating stand. We'll get into what an insulator is. An insulator is that. It insulates. The presence of A, okay, which is a negative charge, induces the electrons to move, to jump. So here I bring in a negative charge. And here I have positive and negatives. Positive and negative, positive and negative. And I bring in a negative charge here. All the electrons want to get out of there. And they do. They jump over here. So all I have left over here is positive. So sphere B is now separated from sphere A. So they were touching. So now I've separated them. B has taken all the electrons. A is just pretty much positive here. And the two spheres there, they have an opposite charge. Okay. So you see, we can play with charges here. The amber effect. This actually came from ancient times. I think it was the Greeks there who noticed there that if you take a piece of amber, you know, a tree sap, that, you know, sometimes they're like, they'll still have bugs and stuff trapped in them. They're like for Jurassic Park, but it's a piece of tree sap that's 1,000,000 years old. And what they noticed there, that you could rub this thing against your hair or fur or something like that, and you could change its charge. And you see here, the amber effect, the comb attracts the beads because it was charged by rubbing it. Okay? We call this there the triboelectric force, which is just a fancy way of saying static electricity. Okay? There's that number again. You don't have to memorize it. You just have to know how important it is. It'll come into play there when we start doing a little bit of calculations. Okay? This is the charge for one proton or electron. You guys will remember this formula there. I can't even remember. It seems like 1,000,000 years ago. Was that week 5? Okay, there we're dealing with the gravitational force of like the Earth or Jupiter or something like this, right? And you'll recall Newton's law of universal gravitation, which gives the size of the force acting between two masses. You'll have a look here at Coulomb's law. The force acting on each of two charged particles, okay, is directly proportional to the net charge of the objects and inversely proportional to the square of the distance. You guys will remember that. You have a look here. All right. You remember what's going on? This formula here is not the same as this one, but there are huge similarities. And that's one of the biggest problems with physics, is trying to get the quantum world, the atomic world, to match up mathematically with the like planets and stars and cars, because atoms and they act very strangely. And but you'll see here that there is some similarities here. Remember how the force, if you double the distance, the force inversely squared goes to a quarter? And we'll go into a nice little recap of these here, but this is your force in newtons. And up here, there, you remember mass 1 and mass 2. Well, instead of mass 1, mass 2, we're going to use charge 1, charge 2. And there's your distance squared. But we're missing one piece of the puzzle, and that's a K value. And this is a constant. Okay? We call this the proportionality constant. Okay? And this is equal to 9 billion. Okay? And it's this number right here. You shouldn't have to memorize it. It's on there. It'll be in any question there that you need. Have a look here, though. The force on Q1 is equal and opposite to the force on Q2. So if I have 2 electrons here, all right, opposite and equal. Well, Q is the quantity of the charge, so how much? I'll show you some examples. I like to use D, but sometimes there you might see an R on the bottom, as you do right here, okay? I think on your... Where is it right here? Yeah. Okay, it's right here. I put a D, okay? These are your formulas there for this week, and you'll see there that I've written them out in triangle form, like we did there at the start of the semester. And we'll go through all these there today. You can see where we're at. You just got to find what I'm asking you, utilize what I gave you, plug it into a formula. You may have to plug it into another formula. It's okay. That's all we're at now. Okay. The proportionality constant. So this is it right here. So like this formula, you remember there from week 5 when we're dealing with gravitational force. There's 1, 2, 3, 4 bananas here. K is always given. Okay, it'll be given in the question. It'll be given on your formula sheet. So I'm going to give you 3 of these. You find me the 4th. That's all this is. An example of this, what would the force be on 2 individual electrons? With 1.6 times 10 to the negative 19 coulombs, each separated by a meter. So, asking for the force. K is given. Sorry, that should be 10 to the 9. Okay. There's my charge there for the 1 electron. There's my charge there for the next. Distance is 1 meter. Square it. There we go. And you look at this number here. This is the force of 1 electron on another electron at 1 meter. 2.3 times 10 to the 28 newtons. Like, there's not much there, is there? Okay, and I actually drew it out, or wrote it out, okay, just to show you. Very, very small force. But they are exacting a force on each other, okay? What would be the force on 2 electrons with 1 coulomb each, separated by 1 meter? So, there's your K value, okay? There's my charge, which is 1 and 1 coulomb. My distance, 1 meter squared. So, if I had 2 electrons, 1 coulomb and 1 coulomb, separated by 1 meter, that's the force acting on them. 9 billion newtons. Just ridiculous. Okay? So, good. That's what we're talking about there. Electric force and Coulomb's law. Okay, the force on Q1 is equal and opposite to the force on Q2. We've seen this there before. So if both objects have the same charge, plus plus or minus minus, then the force is positive. Please remember this. I put these in nice ugly colors so that you guys would see this. Okay, if both objects have the same charge, plus plus minus minus, they're going to repel each other, right? Because the same charge, they don't like each other. So how do we know that they're going to repel each other? Because the force is going to be positive. Okay, now remember, I'm going to give you a charge, okay, for each of, in this case here, 2 individual electrons with this charge. Okay, but what's going to happen here is that's negative and that's negative. All right, negative, negative, negative times a negative is a positive. So that's how we know there that this repels, because the force is positive. If 2 charges are plus minus, in any combination, plus minus minus plus, then the force will be negative because one of those numbers will be negative. So let's say here I have a positive charge, maybe proton. Here I have a negative charge, okay, by an electron. The force that's going to come out is a negative force, okay? That's how we know that these 2 bananas are going to have an attraction to each other, okay? So that one there, very important, okay? Whatever answer there you get for your force, that is how you're going to be able to tell if it's repulsion or attraction. You have a look here. Just as it did there week 5, kind of the same things are going on. And this slide here is highly related to, was it your, yes, it was your assignment. And you'll see something very similar there to your assignment on here. And yeah, your assignment 2 is out and it's live. Paper copies, the e-copies I'll post there. Hopefully they're by the weekend. And that's the plan for that. But have a look here. Here I have 2, whatever they are. Doesn't matter. If I double the charge on one of these guys, now I have doubled the force on both. It kind of works the same way as gravitational force there did in week 5 or 4, whenever it was. You'll remember there, if I double the distance, it's the inverse square. So double 2, and then you drop it below the line, 1 over 2 squared becomes, and so if you double the distance, the force drops to 1/4. Okay? If I triple the distance, the force drops to 1/9. Remember that one? Okay. Coulomb's law and Newton's law of similarity. Okay, remember there that gravitational force between 2 bodies is always an attractive force, right? The Earth and the Moon, Earth and the Sun, it's always an attractive force. But the difference here is that electrostatic forces, you can have attraction or repulsion depending upon their charge. Okay. When you walk across a rug and shuffle your feet, you scuff off some electrons. Are you positively or negatively charged? Well, if you're sloughing off electrons, that means you've lost some negative, so now you are positively charged. How do the mass and charge compare between electrons? Nada. There is no mass change. They're all the same charge. 1.69 times 10 to the negative 19, I think that's what it is. Okay, so there is no difference. What is meant by saying that charge is conserved? Whenever something is charged, no electrons are created or destroyed. They're just transferred. So it's the electrons there that move, and like you have to think, the overall charge of the Earth really doesn't change. Okay, so electrons are all conserved. The charge is always even though you may have two metal balls and that are both electrically neutral, but then you remember you brought the red balloon. Where was that? Right here. And you remember you brought this over, which then all the electrons jumped over here. And then you separate them, and then, wait a second, this ball is positive, this ball is negative. So why isn't the Earth flying out of orbit in chaos into a ball of flames because overall charge is always conserved. It's always there, okay? Within these two balls, it's changed, but generally the charge of the Earth hasn't changed, okay? So that's what it means, our charge is conserved. Where are we here? Number 4. How is Coulomb's law similar there to Newton's law of gravitation? Okay, I think we've kind of covered that. But they are, and I do want you to know that inversely, okay, having to do with the distance. If the distance is doubled, the force will go to a quarter. If the distance is tripled, the force will go to a ninth. If the distance is quadrupled, okay, then the force will go to a 16th. And the differences there for gravitation is always an attractive force, but there for electrostatic charges there we can have positive or negative. How does the magnitude of electric forces between a pair of charged particles change when the particles are moved twice as far apart? There you go. Twice as far, a quarter. 3 times as far, a ninth. Perfect. Charge polarization. If you charge an inflated balloon by rubbing it on your hair and then place the balloon against the wall, it sticks. Why? This is because the charge on the balloon has changed and the charge distribution in the molecules in the wall. You see, the balloon has accepted more electrons. So the balloon is very negative. All right? And you have a look here. You just rub the balloon against your hair. Okay, it just took all these electrons there from your hair, so the balloon is negative. And you push it up against the wall. Well, there's electrons in here too. Like the wall is electrically neutral. There's positive and negative in here. But now you brought electrons there to the party, and you'll notice there that there isn't any electrons kicking around here. They're all, I'm out of here. So now you just got positives, and it should stick. The molecules in the wall cannot move from their relative stationary positions, but their centers of charge have moved. Okay? Now, of course, the molecules can't move. What happens here is basically all the molecules kind of about face. They turn a different direction, and they polarize to accommodate this negatively charged balloon. The positive part of each molecule is attracted towards the balloon, whereas the negative part of the molecule is on the other side. So it does its best there to accommodate. The effect of distorting the molecules of the wall is said to be electrically polarized, while the balloon is electrically charged. Like the balloon is its own beast. It's floating around in the air. It's electrically charged. The wall is connected there to the floor, which is then connected to the foundation and everywhere else. Okay? And it's not charged per se. The wall doesn't change the charge. It just all the molecules kind of about face, and they line up in a certain way, all right, to accommodate the balloon. And we call this there the electrically polarized. Here's another shot of it. Okay. What do we got here? The process of inducing a small charge separation, you'll see the same thing. Okay. You'll see there in the balloon all the negatives. And then the molecules haven't moved. They've just kind of turned around. Okay. And they're showing their feet there, which are positive. And that's how that goes. It works exactly the same way. You guys remember there from chemistry. Water. Okay, it's a polar molecule. Oxygen, very negative. The hydrogens there, very small and insignificant. And water, thank goodness it's polar, or we wouldn't be here. The electric field. The space around every electric charge is energized with an electric field. And this is basically nature's storehouse of electric energy. Storing energy, potential energy. Interesting. The electrostatic force is similar to gravity. The force can act through a distance without the two charges having to touch. It will cause any charged object to experience a force. Okay? And you'll see here what's going on, and there's a force there. We're going to talk more about this there. Have a look. Electric field from positive to negative. The electric field lines indicate the direction that a positive charge would move. Okay? So you have a look here. An electric field about a proton. So this is a positive charge, and the electric field extends outward from it. So, it's good for your assignment. If the arrows are pointing away, that tells you there that that's a positive charge. In the electric field, if the arrows are pointing inwards, that tells you there that this is an electron. So that's where they will line up in this electric field. I'll show you more here. Have a look. And you see, there's a proton and an electron, and you'll see how this works. You'll see there that the electric field extends distally and outwardly from the proton and goes inward and into there and through the electron. Electrically charged and electrically polarized objects are different. Why? Go back to your balloon in the wall. Okay? Number 2. What direction will an electric field be in relation to a proton and then with an electron? There we go. Protons extend out. Okay, and with the electrons there, the field goes in. Find the force of attraction between two spheres, each with plus 140 Coulomb charge, 1.40 Coulomb charge if they are separated by a distance of 0.5 meters. Is it attraction or repulsion? Well, there's your formula. Okay, that's a given. There are my two charges, so it's 1 plus, so it's positive 1.40, positive 1.40. Okay, and here, we use we can use d squared, but that's your distance there. And so we get a positive number here. And that's kind of what we expect, because two positive charges should repel. Okay, positive means they're repelling. Electric potential energy. There we go, potential energy, as I alluded to there before. So as with gravitational potential energy, due to the cyclist's position, we must consider their potential and kinetic energy. Now, I don't know if you guys will remember there, I think from week 1 or 2 there was the football. And how the football kind of moves in two different directions, up and down and left and right. And the whole idea of potential energy, which is stored energy, and kinetic energy, which is moving energy. And you'll see here that a charged particle can and does flow down like water down a river. And it flows up and down here. Potential energy changes to kinetic energy. So you see here we've got kinetic energy. We're moving, all right, and then it's going to get to a maximum here, and basically we're at the highest there that we can go. All right, we have maximum potential energy, stored energy, basically zero kinetic energy, and then it starts to roll again, and then the potential energy changes there to kinetic, and then it rolls down the hill. The electricity kind of works the same way. A charged object has a potential energy by virtue of its location in an electric field. Okay, where the charged particle is will determine its potential energy and see if it can actually do work. Work is required to push a charged particle against an electric field. Okay, so Proton likes to go one way. An electron likes to go the other. We can make them go the other way, but it's just going to cost money. It's going to cost work. Okay? We call the energy possessed by the charged particle that is due to its location, and we call this there your electric potential energy. Okay? And you'll see here that if we put a proton and an electron in an electric field, you'll see which way they like to go. Okay, so anytime a positive charge is in an electric field, it experiences a force in the same direction of the field lines. Okay, so the positive charge wants to go with the field. And the negative charge goes the other way. Okay. If the particle is released, then it just goes with the flow in the direction there that it wants to go. Positive will be with, negative will be against. So if the particle is released, then it goes with the flow where its electric potential energy changes to kinetic energy. So we can hold it there, but then it's at its maximum potential energy. It's like being at the top of the hill there with the bikes. And then you let it go, and then all of a sudden all that potential energy turns to kinetic and it starts to move. Okay. Electric currents. This is a flow of charged particles. The cord on an electric appliance encloses two separate metal wires covered with insulation. Okay, there are two wires inside. If you take a plug off, do it carefully, but you'll see there's two wires inside and it's covered with insulation. When the appliance is plugged in and operating, electrons inside each wire are moving back and forth. Okay, electrons. All right. Now, what I want you guys to know is that this is completely backwards, and that's the only way you'll ever see it. Which I'll get into, we're going to use it in the simple formula there. Okay, originally, whenever they started to develop, electricity and its applications, they actually thought that it was protons moving. And so however many hundreds of years ago, okay, here's your positive terminal, here's your negative terminal. That's on any battery. They originally thought that it was protons moving. So the flow of current is going this way. But the protons, they no move. Okay? Now we know that it's the electrons that are moving. Okay? But for some reason, it's still written this way. So just be careful. Okay? Voltage, which we'll get into. Oh yeah, there's lots of definitions here. Voltage is also referred to as potential energy, electric potential energy. Okay? Kind of acts like the pressure in the blood vessels. So, again, I is your flow, your current of charged particles, and it's actually going the opposite direction there of the arrow. Wonderful. I don't even know if any of you guys would remember an old cathode tube TV. I remember them there as a kid. Okay, and now we have nice, beautiful flat screens. But it kind of works the same way. Inside of a television picture tube, free electrons are accelerated from the back of the tube to the front of the screen. So here is where you would watch your TV, okay? And you'll see there that the flow of current seems to be going this way, but remember there, it's reversed, okay? So there is a vacuum inside the tube so the electrons can travel really without any trouble at all. You guys will know this as well. You would have talked about it there in chemistry. Pure water, distilled water, what do they call it? The red cap there of Culligan's water there. That's deionized. It's just agua. All right, there's no ions in it. That generally will not conduct electricity because the water molecules, there's not enough ions in just pure water there to facilitate a charge. So, but if you put salt, or, I'd say sugar, but no, you put salt or any type of ionic salt and dissolve it into the water, now you're putting positive and negative ions in between the water molecules. So now this thing will conduct electricity. And you'll see here, if an electric field is applied to the water, the positive sodium ions will flow one way, and the negative chlorines will actually flow the other. Interesting, eh? Maybe not. Now here we go, electric current. Here is one of your formulas there, okay? And you'll see here that I is current. Now this is the flow, or the amount of charged particles, okay, per second. So we have the current is equal to the charge divided by time. And current is measured in amperes, A or amps, okay? That's kind of slang, all right? But amperes or A. That's how we measure current. Which an ampere equals 1 coulomb of charge per second, right here. So that is 1 ampere. And you can measure this there with a device called an ammeter. Ooh, that just might be a good little question right there. Okay, so I is equal to Q divided by T. Current is equal to charge divided by time. And you'll see here electric currents, typical currents of common devices, calculator, not much. Spark plug, okay. A 60-watt light bulb has a current of half an amp, okay. 1800-watt hair dryer will have, all right. So you see these here. You can see the relative scale of how much current actually flows through a calculator. Pretty small. Okay. Either positive charges or negative charges can comprise a current. We're just going to deal with negative charges, okay? Formally, an electric current is represented as a flow, okay, of the positive charge. You remember right here? Wanted to show you this one here was better, okay? Originally, it was thought there that the protons were flowing, so that's why the arrow was going this way. But if the arrow is going this way, really, you need to know that the electrons are flowing this way. That's what we're looking for, the current. Okay, the current is always written backwards. All right, good. That's basically all that slide says there. Semiconductors. We all have them in our phones and all this kind of stuff. Silicon, germanium. These are what we call semiconductors. And they're poor conductors of electricity in their pure state, but they can be doped up, okay, to be superconductors. Okay, transistors, solar cells, numerous other electronic components are made out of these, okay, and they're just getting smaller and smaller and smaller and smaller. I think it was the CEO of Intel back in '68 said there that the 6-month rule. These guys here, I think is that every 6 months they're going to double in strength and decrease in half the size. And I think it's pretty much held true over the past 50 years. Resistance. What makes a 100-watt light bulb brighter than a 60-watt light bulb? What is the difference? And it's the size of the current. That's all it is. And this depends on the filament's resistance. So you see that filament there, that magnesium metal alloy strip there that's in your old school light bulb. The electrons would come up and they'd travel across this and in the process make light. Okay? And the amount of light is all dependent on the amount of current that this strip of metal can handle. That's it. So resistance, it's a measure of the opposition to current. So kind of like, I'm not going to say there that current, which is I, is the opposite of the resistance, okay? But it's a measure of the opposition to the current flow, and we'll get more into it there. It's represented there by an R, and it is measured in ohms, okay? And this is your symbol there for ohm, okay? Now, to kind of better understand what resistance is, a conductor, okay, so copper wire, gold wiring, silver wiring, any of these metals there that are great conductors, okay? A conductor will have low resistance, okay? The metal, okay, electricity just flies right through it, almost completely impeded, all right? So conductors, they have a low resistance. An insulator, like wearing rubber boots or rubber gloves there when dealing there with electricity there in the wall or something like that, they have a very high resistance. So the higher the resistance, the closer you are to being called an insulator, okay? Where it stops the electrons from flowing. There are 4 factors that deal with resistance. Composition, the kind of metal, sure, right? Iron wire will have a higher resistance than copper wire. Okay, that's why the number 1 metal that has the lowest resistance is gold, but very expensive. Number 2 is silver, again very expensive. Number 3 is copper. You should try and find those on a periodic table and see there's a bit of a relationship there between them. One is on top of the other, which is on top of the other right in the periodic table. Direct relationship. Another factor is the length. The longer the wire, the higher the resistance. Well, that kind of makes sense. If the electrons got to flow for longer, well, they're going to hit more resistance because they got to travel farther. The diameter of the wire. The thinner the wire, the higher its resistance. You get that? The diameter. The thinner the wire, the higher the resistance, because now you've got less space for it to move through. Temperature. The higher the temperature, the higher the resistance. We're going to get into where we take helium down to like 2 or 3 degrees Kelvin, and you'll see there some of the things there that happens. But the hotter something gets, the less likely electrons are going to flow through it. The cooler something is, the more likely electrons can flow through it. And resistance is similar to friction. Any substance that does not allow the flow of charges through is called an electrical insulator. Plastic, wood, rubber, these are all, they keep their electrons. They do not let the electrons move freely. These are electrical insulators. Conductors, generally think metals. And metals have a weird structure, like you can take a piece of iron, you can melt it down and shape it into a bird cage or a sword, or you can smash it into a piece of iron putty. Metals are malleable. Okay, you can shape them, you can mold them, they're ductile, you can make them into wires in whatever shape you want. Metals are weird in that their electrons are loose. And it's kind of like an electron sea, like an ocean. The electrons are completely free to move within a metal. Okay, that's what makes them there such good conductors. Getting back there to resistance, compared to friction and impedes electric charge, causing heat. We don't want things there to heat up. The larger the current through a particular device, the greater the heat. Kind of makes sense, right? If I want to pump more electrons through this, well, there's a chance there that it's going to get hot real quick. Resistance R measured in ohms. And you'll have a look here. Here we've got a battery. All right? And we've got I'll zoom in here. You got a positive end to the battery and a negative end to the battery. All right? So the electrons are going to flow through here. But remember, your eye, the arrow is going to point this way. I didn't invent it. I'm just the messenger. So in general, a conductor will have low resistance to current flow, and an insulator will have high resistance. Kind of like the same thing as what we've been talking about. Did I miss something here? There we go. What condition is necessary for electric charge to flow? All right. The ends of an electric conductor must have different electrical potential. I'll read that again. The ends of an electric conductor must have a different electric potential. Electric charge in a conductor will flow from a high potential to a low potential. It's just like water coming off a waterfall. The water isn't going to go up. Okay? Things will move from a high to a low. And the water at the top of a waterfall has much more energy in it, capable to do, than water at the bottom of the waterfall. Okay? So without this potential difference, the water will not flow. And in this case here, no flow of charge will occur. Okay, that's just this one right here. Number 2, what condition is necessary for a sustained flow of electric charge through a conducting medium? So we want a sustained flow of electric charge. A sustained electric current requires a suitable pumping device. And I'm going to say that again. A pumping device, which we will call a battery, to maintain a difference in the electric potential. So getting back into here, here's my battery. Here I have a high potential, high electric potential. It's pumping out electrons. This is the top of the waterfall. And the electrons are flowing down. Okay, they're hitting these resistors and coming back. And the potential difference between the negative end and the positive end is just like a waterfall. Okay? And when the battery runs out, as all batteries do, that means there that the water at the top of the falls is shut off. And the electric potential between this side and that side, there is no difference, so therefore the taps are turned off. Okay? Good. Geez, man, we're moving. We were talking there about superconductors. Remember there we were talking about the gallium and silicon and all these guys. It's quite interesting there to see that most elements... Well, here, I'll just be quiet and read it. In 1911, Dutch physicist Heike Oens, using mercury, discovered that the resistance decreased steadily at a temperature as the temperature was lowered. So this guy's using mercury, and the resistance is decreasing as it gets colder, and pretty steadily too. So it gets easier and easier and easier for electrons to flow up until about 4.2 degrees Kelvin. So what is that? 273 minus 112. So at minus 268.8 degrees Celsius. And I mean at this temperature, now this has become what we call a superconductor. It's like there is nothing there. The electrons flow with zero resistance. Electric current is flowed through the mercury with no resistance, and we call this is a good word, critical temperature. So every element will have a critical temperature. It's like density. It's like it's a property of an element. And what happens there, as you cool the element, okay, the hotter something gets, the more resistance we get, right? The cooler something gets, the less the resistance gets. I can get more electrons flowing in there, the cooler it gets. And it's pretty steady, But then at a certain temperature, the critical temperature, the resistance falls to 0. And now the electrons flow absolutely unimpeded. Uses, there's lots of uses there. I love this one there. The Hadron Collider there in Switzerland. Just incredible at, this thing is what, 15 kilometers underground. And they've already made some amazing discoveries there, like the Higgs boson particle. Yeah, give that a quick Google search anyway, just for fun. MRI, magnetic resonance imaging. There's another reason why we use superconductors, available in every hospital. Electric current and Ohm's law. An electric current will flow in a light bulb, okay, a radio, or other such devices only if an electric field is present to exert a force on the charge. Okay, let's read that again. An electric current will flow in a light bulb, a radio, or other such device only if an electric field is present, which exerts a force on the charge here. So, you have a look here. There's your current flow, which really is the other way, right? So the electrons are flowing up here, okay? And a flashlight works because the batteries produce an electric field that forces the electrons to flow. And that's what this is all. There's your electric potential energy, right? It all has to do with the battery producing the electric field. And once you have the electric field, that's slide 53. Once you have the electric field, wham, they start to move, right? Go with the flow. Now, what was that, 53? Yeah, this is a long PowerPoint. I apologize, but you guys can start and stop it. I'm just going to go right through before my kids get home. Oh, dear. An electric circuit is any such system consisting of a battery or another power supply, like the wall, some electrical device such as a light bulb, and wires to carry the current to and from. So this could be the wall, there's your wire, there's your light bulb or your laptop or whatever it is, right? There is your electric circuit, just like the Formula 1. Here we're getting back into the battery, that pump, that charge pump. The power supply acts like a charge pump. So your battery, it forces charges to flow out of one terminal, go through the entire circuit, and back into the other end of the terminal. Electrons typically move through a circuit quite slowly, about 1 millimeter per second. Okay? So in this respect, an electric circuit is much like a cooling system in a car in which the water pump forces coolant to flow through the engine, radiators, and hoses. Okay, I don't really think that's the greatest analogy, but you kind of get the point. Okay, so an electric circuit, it's just going through the entire system. Okay? How it does that, though, is a little different. The concept of energy and work are used to quantify the effects of a power supply in a circuit. So in a flashlight, for instance, the batteries cause electrons to flow through the bulb's filament. Makes sense. In a flashlight, the battery causes the electrons to flow through the filament there in the bulb, which causes the light. Because a force acts on the electrons and causes them to move through a distance, work is done on the electrons by the batteries. So the batteries are getting the electrons to do work. They're moving. And you guys have seen that there. And work. This time here, work, electrical work. All right? But what we have here is voltage is equal to work divided by charge. And that's written, where's my voltage? Work and charge. Okay? And you guys know how these work. If I'm looking for voltage, I put my thumb on voltage. Voltage is equal to work divided by charge. If I'm looking for work, I put my thumb on work. Work is equal to voltage times charge. Okay? So there's another formula. And yes, this is work, electric work. The energy per unit of charge given to charged particles by a power supply. The SI unit of voltage is the volt, which is equal to 1 joule per coulomb. Okay? Voltage is measured by what's called a voltmeter. So here's your charge pump. This is the actually, I guess I will do it right now. The battery is the volt and electric potential energy. Battery, electric potential energy, volt, all kind of mean the same thing. The difference in charge between the 2 points, the top of the waterfall, bottom of the waterfall. Sorry, I think this is a negative, top, bottom. So in a question, you might see, find the potential difference. This means find the volts. And I wrote these on here because I don't want you guys to get mixed up. If you're going to make a mistake, just don't make a mistake. But what I want you guys to do is that I may ask you, for the following situation, find the potential difference of this, blah, blah, blah. Well, what do you mean the potential difference? What am I looking for? If you see potential difference, it means I'm asking for the volts. Okay? If I'm asking for the electric current, I'm asking for I, which is amperes. Okay? Resistance. Okay, I kind of given you guys a little bit of help here because this is all new stuff. And I don't want to see you guys lose marks. So if I'm ever asking for the potential difference, I'm really asking for the volts. And the reason why I'm telling you guys this is because verbally, potential difference sounds a heck of a lot different than volts. But really, that's what I'm looking for. The pump, the battery, okay, in volts. Common voltages, okay. A nerve impulse is about 0.1 volt. A D-cell battery is about 1.5. Car battery, 12. Wall socket, it can vary, 120. Here's your TV, 20,000. Power plant, generator, okay. High voltage there, you see them on their way down to Toronto. Okay, very dangerous stuff. So a 12-volt battery gives 12 joules of energy to each coulomb of electric charge. Let's read that again. A 12-volt battery gives 12 joules of energy to each coulomb of electric charge that it moves through the circuit. So a 15-volt would give 15 joules of energy to each coulomb. Okay, you see what's going on here? Each coulomb does 12 joules of work as it flows through the circuit. Each coulomb does 12 joules of work. All right, we've got some questions here that I'll show you. If we return to the analogy of a battery as a charge pump, the voltage plays the role of the pressure. Okay, it's the difference. It's the potential energy, the top of the waterfall. A high voltage causing charges to flow in a circuit is similar to a high pressure causing a fluid to flow. So here I have my pump with water. All right, and if I increase, okay, the voltage, if I increase the pump, the water's going to start kicking. And then you see right here, this is a resistor now. We've decreased the surface area. The water here is, the resistance there, very, very high pressure there, and we're moving it through. And similar there to the resistance there. Okay, so I want you to think of the battery as the pump. Okay, it can, depending upon the voltage, the higher the voltage, okay, the higher the pump. Even when the circuit is disconnected from the power supply and there is no charge flow, the power supply still has voltage. So you can take the battery off and let it sit there for 6 months and then put it back in, okay? In this case there, the electric charge is basically potential energy. There's your electric potential energy. Voltage is also referred to as electric potential energy. Here's another formula. It's not too bad. Okay, you've seen this one here, you've seen this one here, and you've seen this one here. Just put it in a different way. V is the voltage in volts. I is the current passing through in amperes. R is the resistance in ohms. Okay, and the size of the current that flows through a conductor depends on its resistance and on the voltage causing the current. Okay, and here's just another shot of it there. The higher the voltage for a given resistance, the larger the current. The larger the resistance, the smaller the current. So they kind of work on opposites. And you can have a look here. Try these out. They're not bad at all. All right, and I didn't even put what's what I'm looking for? Step-by-steps. Because you've got one of these little formulas there. I have no idea how it's written. Where is it here? I over V, and there's your resistance there. Okay, it's all here. Plug and play. So you can have a look at those, and let me know if you have any issues with these guys. Again, same questions. There's a little bit of work there that you guys can see. Okay, let me know. Email me if you have any trouble. Electric shock. What causes electric shock? Is it current or voltage? Current. The resistance of one's body depends on its condition and ranges from 100 ohms if soaked to about 500,000 ohms if very dry. See if that makes sense again. The resistance of one's body depends on its condition. So if I'm wet, the resistance is only 100. If I'm dry, my resistance is 500,000. So I'm pretty safe here. Not so here. If we touch two electrodes of a battery with dry fingers, we offer a resistance about 100,000 ohms. You'll make it. You're okay. We would not be able to feel 12 volts, and 24 volts would barely tingle. If we repeat this with our skin being wet, 24 volts would be extremely uncomfortable. Okay, so that's kind of a little interesting little bit of information. Electric shock, as we said there, it's all about current, and you can have a look here, 0.001, you can feel it. 0.005 can be a little painful, and up here we're into cardiac arrest. Okay. Electricity current will always travel the path of least resistance. So if your electricity is here, it wants to get here, it will find the shortest way. If you grab onto an overhead power line with both hands, you will not be shocked as long as you do not touch anything else that may have a different electric potential. Right? You in this type of a situation there, basically there's no way for the water to travel down the waterfall. Okay? So that's okay. So there's no need. It's okay. And this is because no charge will flow from one hand to the other. If, however, you ground yourself, and what do you mean by that? Touch something else that has a different electric potential, now you've given the electricity reason to flow through you. Okay? Just an example of an open circuit, and you'll see that the light bulb is not on. Battery here, okay, electric potential energy in volts, it's got juice in there, but because this system is closed, nothing can flow. So therefore now no electrons are passing through the light bulb, so the light bulb is off. If we close the switch there, all right, yeah. If we close the switch here, the light bulb will only light if the circuit is closed, because now we have a flow. Okay. Any path along which electrons can flow is a circuit. For a continuous flow of electrons, there must be a complete circuit with no gaps, of course. This is where we get into, there are two kinds of circuits there that I want you guys to know. Okay? One of them is series. So in a series circuit, there is only one path for the charge to follow. So the same current flows in each device. So you see your current says it's going this way, but really it's going this way here. And all the electrons are flowing through. There's only one path. Now, there during the holiday season, it's really bad to have lights like this, because if one light goes, then they all go, right? So this is interesting to note. So in a series circuit, the voltage is divided, okay, among the devices. The voltage in all devices equals the voltage of the power supply. So for example, if 3 light bulbs with the same resistance, and they have resistance because the electrons have to go through it, so they're offering some resistance here. If the 3 light bulbs with the same resistance are connected in series to a 12-volt battery, the voltage on each bulb is 4 volts. All right? So that's in a series circuit, you find the voltage for each bulb divided by the number if they're all the same. And here's the whole holiday light experience. Okay, if one bulb goes out, all of them go out. To counter this there, we have what's called the parallel circuit. In a parallel circuit, the current through the power supply, the current this time, is divided among the devices while each has the same voltage. The current flowing in all devices equals the current output by the power supply. Well, okay, the current going in, the current coming out is equal to the current going in, but they're divided by each one. If one of the devices burns out, as in this case right here, these guys here are okay. All right? As more devices are connected to a circuit, more pathways for current result. Current and resistance are inversely proportional. This lowers the total resistance of the wire because you're basically making a bigger wire. Okay? Circuits that carry more than a safe amount of current are said to be overloaded. Now, this is where we can get into trouble. Connecting too many devices in the same parallel circuit results in overheating of the wires, which may start a fire. Okay? 3 light bulbs are connected in a parallel circuit with a 12-volt battery. The resistance of each bulb is 24 ohms. What is the current produced by the battery? Well, current is I, and I gave you V and R, so the current is 0.5 amps. The total current supplied by the battery equals the sum of the current of the 3 bulbs, right? Because we are in a parallel. So in this case here, you just have to know, and you make notes on these right here, of the differences there between a series and a parallel. Okay? And in this case here, what is the current produced by the battery? Well, we know the current there in the 1 bulb, there are 3. Okay? So 3 times 1.5, or 3 times 0.5 is 1.5. Okay? The current flowing in the first device plus the current in the second and so on equals the current output by the power supply. Okay? Then that kind of makes sense. Okay? The current here plus the current here plus the current here has got to equal the current going in and out.